theoretical frameworks of how to do some of these calculations within the arena of like SIDM, which for me is going to be self-interacting dark matter. And in particular, some kind of the theoretical output of some of these things is what I named the quantum mechanics swampland. And then towards the end of the talk, I'll also touch on some future directions where we're using this framework to kind of come up with these, basically do these robust calculations using the framework that I developed, and then use that for more phenomenological and astrophysical implications of what we're doing. All right. So just to get started with a brief overview of SIDM. So, as I mentioned, this will be self-interacting dark matter. So what I'm really going to focus on are basically perturbative field theories in the dark sector where you have some kind of interaction. For the time being, I'll be agnostic specifically about what the interaction is, because the aim of this is going to be to build up a framework where you can kind of apply it broadly to, however complicated you want to make your dark sector. Right. So, before I start talking about the framework, why do we actually want interactions in the dark sector, right? So kind of as many of you may have heard, there's lots of discrepancies between these dark matter only simulations and observations. And depending on which simulator you talk to, they may argue that everything's explained by baryons or nothing's explained by baryons. So, it's an open arena, but kind of just to give a flavor of some of these, these tensions as such are, so the first is the diversity of rotation curves. So basically, if you look at, the rotation curves of galaxies in these dark matter only simulations, they're pretty well correlated. You kind of get a very tight band of what these rotation curves should look like. But if you go out and, observe them, obviously you see a huge scatter where they don't have, they don't all flatten out. Some of them increase as you get further and further away from kind of where the luminous halo ends. So you kind of get a large scatter in the shapes of these, rotation curves. And these DM-only simulations often have trouble explaining that. There's a too big to fail problem. So some subhalos around Milky Way type galaxies in these DM-only simulations should basically just be so big that at some point they should have accreted stars or accreted, baryonic matter, formed stars, and we should have been able to see them. You have a mismatch between how many you see and how many you don't see between the simulations and observations. And this kind of ties in also to like the missing satellites problem, where basically we have an underprediction of how many satellites, we have an overprediction compared to how many we observe of how many satellites there are. And then finally, there's something called the core versus cusp problem, which is basically just saying that if you were to map out within these different halos what the dark matter distribution looks like, these simulations expect you to kind of get a cuspy behavior, which sort of diverges as you get closer and closer to the center. So you basically get, really, really dense cores or like centers of galaxies and halos. But if you go out and actually do observations, you end up finding that they tend to flatten out towards the center. Right. So there's all of these discrepancies. I'm not going to plant my flag on one camp or the other and tell you that, these are kind of the, end all be all for why we need SIDM. In particular, there's kind of two huge caveats to all of these statements I'm making. First of all, there's going to be observational biases that you need to take into account, right? Like maybe the missing satellite problem is we're missing satellites just because they're too small for our current detectors. But if we improve detectors, maybe we'll find all of them, right? So like there's observational biases like that need to be taken account. And then the other main thing is that I'm comparing observations to simulations that only have dark matter, right? So if you start throwing in baryonic physics, now, how do you model all of that properly? It tends to be difficult, which is why people do DM-only simulations to kind of get a first answer at, what's happening. But really taking into account baryonic effects can make major differences in all of these things, right? So kind of observationally and experimentally, you have all of these things to kind of take into account. But as a true theorist, I want to take a step back and, and kind of flip it on its head a little bit and say that every particle that we have in the standard model has some interesting, gauge interactions. So why do we expect the dark sector to be kind of completely, non-interacting and boring, right? So if that's the case, and if you're willing to kind of, take that as the motivation for why we think about this, then the next question is, how do we start teasing out what these interactions are in the dark sector, right? So there was this interesting paper in 2015 by Manoj and collaborators where they basically pointed out that if you were to take systems of differing sizes, then effectively in these different systems, you have differing virial velocities. So you can basically start to map out what the self-interaction cross-section should look like as a function of velocity, right? And so, if we have more robust measurements where we can actually tease out what these cross sections look like, all of a sudden you can start mapping this out. And then the question becomes, what is your underlying dark matter microphysics that can actually lead to this, right? So like if you look in that plot, there is a yellow dotted line where they're basically fitting that data to a Yukawa mediator with certain masses and interaction strengths. But even by eye, you can kind of actually draw a whole bunch of different curves through it, right? So now the question is, which curves are motivated from an underlying microphysics model versus what is something that I'm just kind of drawing on this plot. And then the other thing to point out is that we're in the regime where everything is non-relativistic. And here you need to take into account Sommerfeld enhancement, because that's something that can greatly enhance these cross-sections and make it something that if you have some kind of non-trivial velocity dependence just from a tree level cross-section, that's also going to get modified. So you need to, account for those effects to make sure that you're kind of actually capturing the physics accurately. So to explain Sommerfeld enhancement, I think, a classical analogy, I think, is kind of one of the best ways to do it. So imagine you have a disk of radius r, and you're throwing a test particle at some velocity v. Now, if you don't have gravity or any kind of attractive force between these objects, the cross-section is just going to be the cross-sectional area of the disk, so it's pi r squared, right? But now imagine this is, the sun, and you're throwing a comet at it at some velocity v. What is the cross-section of interaction? Well, it depends on the velocity, right? So more specifically, it depends on something that we learn in classical mechanics called the impact parameter, which if you recast in terms of the kinematics of the system, you basically get this factor in parentheses where you have a 1 over v squared dependence, right? And intuitively, this makes sense. If something's moving really slow, it's going to hit the sun. If it's moving by really fast, it may deflect a little bit, but it's going to basically keep going on its current trajectory, right? So, the idea is effectively the same. So, how do you actually treat this? So it's a non-perturbative effect. And the reason that it's a non-perturbative effect is because, you naively would think that to just estimate the leading order cross-section, you have to take the tree level exchange between the two particles, and that gives you what the interaction looks like. But what Sommerfeld enhancement basically tells you is that you actually have to sum up an entire ladder of diagrams. So you have to consider the 2 exchanges and 3 exchanges and so on and so forth. And if you resum this entire ladder, that's what gives you the true scattering cross-section. So in that sense, it's non-perturbative, and you can treat it quantum mechanically by basically saying that, all right, I'm going to take my tree level single exchange potential or single exchange matrix element, convert it into a potential, and then solve the Schrodinger equation using this. And if I do this calculation carefully, then I'll actually get the entire entire cross section where I'm resumming this entire ladder. Okay, so with regards to this, I'm going to take 2 case studies. I'm going to take the scalar exchange and the pseudoscalar exchange. So the scalar exchange is the well-known Yukawa potential that we all know and love. The pseudoscalar exchange is a horrendous mess. So you get delta function terms, which I've omitted here just to, there's S-channel delta function terms. There's also delta function terms that arise from the T-channel exchange. And more importantly, there's this 1 over RQ potential here, and that's going to be kind of the biggest source of pathologies that we're going to have to deal with, right? So for those of you that are, either teaching quantum mechanics or have taken it recently, 1 over RQ potentials are bad. And the reason for this is because they're not well defined at the origin, right? So the way that you set up the calculation with Sommerfeld enhancement is to basically figure out how the wave function of this 2-particle state is being modified by the presence of the potential at the origin. And that's what's giving you the Sommerfeld enhancement factor. But if you have a 1 over RQ potential, that's not a problem that you know how to solve anymore, because it's a very ill-defined differential equation that you're trying to solve. So the question then becomes, how do you set well-defined boundary conditions for potentials of this form? So this is one of the main results of the first paper in that series of papers that I listed before, which was this matching prescription that we came up with, right? So the main idea is that when you're starting to get close to the origin, you're really probing momenta that are semi-relativistic or fully relativistic. At which point this non-relativistic matching that you did between QFT to quantum mechanics to get your potential, you should expect that to break down, right? So there's no reason why you should trust that on those short distance scales. So the idea that we came up with was to basically say that, all right, in that region where, for R less than A, which we set to be the Compton radius of, the Compton wavelength of the particle that's being scattered, for those regions, we're going to take the QFT description of the scattering process, use that to set the boundary conditions at R equals A. And then from there out to infinity, we can basically solve the Schrodinger equation. And that should capture the Sommerfeld enhancement that's occurring at the long distances. So in particular, one of kind of the hidden assumptions that I'm making here is that in this region over here, you don't have any significant Sommerfeld enhancement. And so you really can approximate it as a tree level scattering, which basically corresponds to taking momenta to be larger than the coupling alpha. So in regions of parameter space, and we can explain that a little bit more analytically later on, but effectively that's what it amounts to. So as long as we're in regimes where that condition is satisfied, you don't have significant Sommerfeld enhancement in in the short distance regime. So the tree level QFT is a good description of what's happening. We take that to set the boundary conditions, and then from there, we'll take we'll solve the Schrodinger equation, and everything is well defined and non-pathological. Okay, so to kind of do this a little bit more, like put some numbers to it, how do we go about doing this? Well, in particular, we know that the first Born approximation in quantum mechanics is actually a very good, faithful reproduction of this tree level QFT. So sort of functionally, what we're doing is we're taking this long range potential, we're computing the first Born approximation with it. And, this K matrix that I'm putting here is just it's basically a multi-state generalization of the phase shift. So if you were to take like the one state version of it, this is basically the equation for tan delta L. But this is basically a multi-state generalization of it. And so the idea is that you can compute this K matrix, and then you can use that to determine how the wave function is being altered by the physics in that regime from 0 to A. And then once you do that, you can you now have basically captured the physics from 0 to A using this method, and then that's telling you how your boundary conditions are being modified. And once you have these new modified boundary conditions, you can then use that to solve the Schrodinger equation from A out to infinity. Is there any questions so much? The fact that it's rising with velocity? Yeah. So that comes from the fact that if you take the non-relativistic limit, there is a velocity dependence in the numerator. So it basically scales like s dot q over q squared plus m squared. So for the tree level scattering. So at low velocities, it's being dominated by 1 over like v squared over m phi squared. And then at large velocities, yeah. So that's where that behavior comes from. All right, so we'll actually start using this prescription to compute some numerical results. So the first test case, like I promised, is to use scalar exchange. Now the scalar exchange is really nice because the Yukawa potential is actually completely well defined at the origin. So you don't actually have to do all this matching prescription that I talk about. What you can do is literally just blindly set boundary conditions at R equals 0, solve out to infinity, and see what answer you get. And what ends up happening when you do that is you actually get the exact blue curve that I have labeled as the numerical cross-section. So using our prescription, which is what the numerical cross-section is, and comparing it to, what you could just do blindly and without doing this matching prescription, you actually end up reproducing the exact same results. So it gives us confidence that, what we're doing is not completely wrong. And there is the physics insight that we're putting into this is actually something that isn't breaking down in some region of parameter space. The other thing to point out is that so the orange curve, or red, depending on how it's showing up there, is the tree level cross section just by taking the single exchange in field theory. And what you end up noticing is that at low velocities, you actually get a significant enhancement between the two. So this is really showing you that Sommerfeld enhancement is kicking in at low velocities. You're getting a massive jump in the cross section because of this effect. And the other thing to point out is that with and without the matching procedure, the numerical results for the full answer still agree. So it kind of gives you confidence that, okay, we can actually do this, right? So then the next thing to do is to start thinking about pseudoscalars, right? So here you don't have that liberty of just setting the boundary conditions at origin, because if you do, then you need to either renormalize the Schrodinger equation or figure out some other way of kind of regulating it, and it becomes a whole mess, right? So here you really are kind of stuck with only using the matching prescription that we described. So if we do that, what you end up finding again are this, with our prescription, we get the blue cross-section curve, and then the orange is again the QFT tree level cross-section. And what you end up finding is that there is no Sommerfeld enhancement at low velocities. And actually these two curves pretty much overlay each other exactly out to high velocities. In particular, you'll notice a slight deviation at velocities of about 0.1. And numerically, that amounts to about a 1% deviation. And that's entirely coming from the fact that the potential that we used to do this calculation was the leading order in the non-relativistic expansion. So the next order correction would be order beta, which in the cross-section would manifest as beta squared. So it's entirely being saturated by the fact that we just took a leading order non-relativistic expansion to compute this. So, we find no Sommerfeld enhancement at low velocities, and that may be kind of surprising, but, heuristically, I'd argue that this is actually effectively a short range potential, right? And so kind of the way to see that is there are 1 over r cubed and 1 over r squared type pieces in this potential, which effectively will die off very quickly with large distances. So that shouldn't be super surprising that those things behave like short range potentials. But then you might ask, what happens about the 1 over r type pieces, right? So you have something here that looks exactly like a Yukawa term, and the last term in that, at the end of the square brackets is also scaling like the Yukawa term. So why aren't these things generating Sommerfeld enhancement? So in particular, Sommerfeld enhancement comes when you have a light mediator, right? That's when you really get a long range force. And when we say light, we mean light relative to the particle that's being scattered. So what ends up happening is the regime where you would expect Sommerfeld enhancement to start turning on is precisely the regime where this m phi squared over m chi squared, will basically suppress and just kill that term. So, and then in the regime where m phi is large, where you just have a heavy mediator, you expect this to not be a long range force either. So basically, all of the terms that are showing up in this potential will effectively behave like short range potentials. So this is kind of the reason why it's maybe not super surprising that you're not getting a Sommerfeld enhancement. So there was a lot of heuristics. I promise that's not all we argued in the paper. So there's a way of doing this a little bit more analytically, right? So you can actually do this using Feynman diagrams. In particular, the whole point of the Sommerfeld enhancement is that you get ladder diagrams like the one shown here, where these things are either comparable to the tree level or even larger in some cases. And so what you need to do is, if that's the case, then you need to actually sum up the entire ladder. And so what ends up happening is you can, basically just take it for the pseudoscalar case. In the non-relativistic limit, the T-channel exchange is velocity suppressed. So this is, going back to what Bhaskar was asking earlier. So the dominant contribution in the non-relativistic limit is going to be the S-channel exchange for what we're looking at. And so if you do this comparison of the one loop to the tree level diagram, you essentially end up getting this naive log enhancement, right? And so this is something that we know how to do this resummation properly. And so you're not actually getting a significant enhancement. As opposed to that, if you do the same argument for the scalar case, what ends up happening is in the non-relativistic limit, the T-channel diagram is the one that dominates because that scales just like 1 over q squared. In the non-relativistic limit, that thing dominates. And then when you take this ratio, you end up finding that the one loop answer will be larger as long as m phi is less than alpha m chi. So this is, if you're familiar with the Sommerfeld enhancement literature, this is usually the condition that's enforced as the regime where you need to take into account enhancements versus where you can just take the tree level exchange. So basically, even more rigorously and analytically, you can essentially derive the conditions for when you expect this enhancement to be relevant versus not relevant. Okay, so with this in mind, it then kind of brings, just stepping back a little bit, now that we have this formalism, we can maybe ask just some more general questions, right? So first of all, is the pseudoscalar potential actually singular, right? So it looked like 1 over r cubed. It looks like it's diverging really fast at the origin. So it does bring up the question of, hey, maybe this is actually a problem, right? But the formalism that I talk about seems to handle this without any issues. I don't actually get things, blowing up at anywhere in the calculation. So maybe it's not actually singular. And more importantly, if you have a singular potential, does this actually have any implications for phenomenology, right? If it's singular, do we care that, we're using this as a description, or do we need to somehow kind of refine this? And in particular, if you kind of go literature digging back to like the 60s and 70s when people were thinking about these questions, you end up finding lots of reviews that basically try to classify singular potentials using two, main classification schemes. So the first was just a blanket statement based on the power law divergence of the potential. So anything that goes faster than 1 over r squared at the origin is singular. So according to that, classification scheme, the pseudoscalar potential that I talked about would be singular. And then the second, which came a little bit later, basically said that if your potential is coming from non-renormalizable operators, then that's going to give you a singular potential. Whereas if it's coming from renormalizable operators, then it's going to be, non-singular and everything's fine and good. And I will draw a counterexample to that as well in the second half of the talk. And then, if you kind of fast forward to, within maybe like the past like 5-10 years, people have claimed that you can also get Sommerfeld enhancement, and you can have implications with these singular potentials for things like SIDM scattering and Sommerfeld enhancement. And in particular, what this paper did was basically said that, okay, I have a 1 over r cubed potential that's going down to the origin. I don't know how to treat this. So what I'm going to do is I'm going to replace it with a square well potential. And essentially go down the route of kind of regulating the Schrodinger equation and then doing some kind of renormalization to make sure that the results are robust. And in particular, what they do is they allow the depth of the square well and basically the coupling strength to just be free parameters. So essentially what ends up happening is they claim they find Sommerfeld peaks, and those peaks are essentially coming from this square well potential having near threshold bound states. So anytime those near threshold bound states cross 0, you start, you see the Sommerfeld peak, and they claim that it has implications. But because they're allowing these things to be free parameters, they're not actually matching it to a perturbative QFT. And so this is essentially the reason where their analysis starts to kind of break down. All right, so I'm going to do a hard pivot into swampland stuff. And part of why I'm introducing this is just so that I can borrow all their terminology without, actually explaining things. So the basic idea of the swampland is, essentially consistency, right? So kind of you have this like abstract theory space where you just have a lot of different field theories that are floating around at low energies. But if you were to kind of look at higher energies, so if you were looking at like the quantum gravity scale, only a particular subset of these things can actually be UV completed into quantum gravity, right? So the whole idea of the swampland program is to say that, all right, we should only focus on the things that live in the landscape. Everything else is in the swampland, and we just throw it away because it's going to develop some kind of pathology. And the way to kind of figure out whether something is actually consistent or not is you want to frame these conjectures in terms of criteria that the low energy field theories have, right? So you don't want to have to do all this work of actually figuring out what theory of quantum gravity something's being completed into, because that's difficult. So all you're saying is, all right, I just have certain criteria that I know my low energy theory needs to satisfy. If it satisfies it, I know it's not going to be pathological. If it doesn't, we're going to throw it away. So what I'm going to do is basically apply this exact philosophy to study quantum mechanical potentials, right? So I'm going to take a step down and do essentially the same picture, except replace string theory and quantum gravity with tree-level QFT, and then replace this entire landscape and swampland at the bottom with quantum mechanical potentials. Right? So for me, the landscape is going to consist of all quantum mechanical potentials that can be derived from well-defined tree-level QFTs. So that's going to be what I'm going to consider to be in my landscape. Strictly speaking, this is a very restrictive definition. In general, there may be ways to kind of expand this, and this is something that I'm kind of currently thinking about, but at least for the purposes of this talk, that's going to be kind of my area of focus. And so according to this, if a potential will live in the swampland, so it'll be a bad potential if it's singular, right? So now the next step is, all right, we're shooting for consistency here. So we have the consistency part. So the next step is you want to figure out what is the diagnostic that you can put down in terms of the low energy field theory or low energy quantum mechanical potential. So for me, the diagnostic that I'm framing is to say that if the first Born approximation diverges for any combination of incoming and outgoing states, then the potential is singular, right? So in particular, this is the K matrix. It's an integral from 0 to A of that product of spherical vessels, which are basically the free particle solutions in 3+1 dimensions, times the potential between those two states. And in particular, K is effectively the mass of the external particle times the velocity. It's the momentum of the incoming and outgoing states. And A scales like 1/m chi. So the arguments are always going to be small. So you can do a non-relativistic expansion of these SLs and SL primes, or a small, correspondingly a small argument expansion. And you end up finding that it scales like, it has the following R dependence. And in particular, that tells you that basically the lowest angular momentum states are going to be the ones that are probably going to be the most pathological, right? Which should, again, make sense because those are the ones that are actually being able to probe the origin, right? So like the S wave can actually get to the origin, and everything else has, more and more support near the origin. In particular, for L and L prime equals 0, you end up finding that anything that scales worse than 1/r squared could potentially blow up, right? So that's something that we need to be a little bit careful about. So as examples, we'll use the pseudoscalar potential and then basically the non-renormalizable version of that same story. And that'll kind of go back to the two classification schemes that I mentioned earlier to kind of really show whether these things are singular or not. So the first one is going to be the renormalizable version of it, right? So this is already the potential that we saw. And I've just to kind of make things a little less clunky, I've basically thrown away the delta function terms because those ones, I'll argue in kind of the next part why they're okay. But you end up finding there is a 1/r³ piece. So we're going to test that part out. And essentially, if you just plug it into your diagnostic, you end up finding that the integral scale is like r to the L plus L prime minus 1. So for L and L prime equals 0, that's going to be a state that's going to cause us problems. And surprisingly, what ends up happening is if you actually evaluate the matrix element for that operator between those states, it vanishes. So essentially, the only problematic state that we had, showing up is actually killed off entirely by this operator structure. And so this is part of the reason why, when you're talking about these potentials, it's not sufficient to just look at the radial dependences. You need to actually take the entire potential. So if I didn't have that operator structure, a 1/r³ potential, without any operator structure would be singular. So according to my classification, it would actually end up in the swampland. But because I have this operator there to kind of save the day, you end up finding that, this pseudoscalar potential is fine. Now, maybe this shouldn't be super surprising, right? Because at some point during the talk, I'd argued that the tree level QFT answer is faithfully reproduced by the first Born approximation, right? So entry-level field theory, pseudoscalar exchange is finite. So you better get a finite answer here, right? So this is, a different manifestation of essentially the same criteria. And it's kind of telling you that you can't just throw away information when you're doing this computation in quantum mechanics. So next, I'll do the non-renormalizable version of it, right? And so this is effectively, if you compute the potential, it kind of comes out to spin matrices dotted into derivatives acting on a delta function. So it's a contact term. It will transform into a delta function. You run your diagnostic again, and what you end up finding is if you're, do everything carefully, you essentially end up getting this kind of gigantic mess down here in the second bullet point. And the key takeaways here are there's basically two different cases where things could be problematic for us. So the first case is when L and L prime are both 0. If you plug those in, you essentially end up recovering the exact same operator that we had before. And so now when you take the matrix element between those two states, it vanishes and you don't have a divergent show up. The other case is when L and L prime both add up to 1. So it's either 0, 1 or 1, 0. And if you plug that in, you end up finding that that term in square brackets actually just entirely vanishes, right? So even in the non-renormalizable version, this kind of classification that said that if it's showing up from an operator with dimension greater than 4, it's singular. Here's a concrete counterexample where you're getting, perfectly well-defined answers, and you can actually do this calculation entirely robustly without any infinity showing up or without any kind of renormalization that's required. Okay, so then you might argue that, all right, in all of these things, it seems like you're getting some nice operator structures that are basically coming to save the day, right? So what if I just throw away all the operator structures? So the cleanest and nicest example of that is to do the Coulomb potential in just arbitrary dimensions, right? So basically it scales like alpha over r to the d minus 2, where d is the number of spatial dimensions. So basically anything with d greater than 4 will scale faster than 1 over r squared. And then according to the classification scheme that said those potentials are singular. So that would mean that Coulomb potentials in higher dimensions are basically singular. So to compute the diagnostic, if you recall, what we were doing was sandwiching the potential between these states, which I had called SL and SL prime, which are basically the free particle scattering states. So what we need to do is, solve that problem for, d spatial dimensions. And so you can start with writing down the free particle Schrodinger equation. And if you solve it, what you end up finding is that instead of doing a radial function times spherical harmonics, which is what we're used to in 3 plus 1D, in arbitrary dimensions, that becomes still a radial function times these things called Gegenbauer polynomials, which are basically just kind of higher dimensional generalizations of this spherical harmonic. And so, do some algebra and some massaging, you essentially end up finding that you can kind of reproduce the exact same type of free solution for the radial equation, except the only difference is that the argument of these spherical Bessel functions that are there now depends on the dimension that you're working in. So instead of just being angular momentum L, they're now dependent on L plus d minus 3 over 2. So if this is the case, now what I can do is take this Coulomb potential that's in d spatial dimensions and run our diagnostic. And essentially, if you just kind of plug and chug through all of it, what you end up finding is that the dependence on the number of spatial dimensions actually completely drops out, which tells you that the free particle, the Coulomb potential in arbitrary spatial dimensions will actually be, well-defined, and it'll give you a finite, well-defined answer, and you can actually compute it, which again, should sort of intuitively make sense if you're just looking at this from a field theory perspective, because Coulomb potentials are arising from scalar or vector type operators in arbitrary dimensions, and those should give you finite, well-defined answers, right? So the fact that you're kind of seeing this should maybe not be as surprising, but it does tell you that this criteria that you're using to kind of, determine whether things are singular or not really needs to be refined, and you need to kind of think carefully, especially if you're thinking about this from a field theory perspective. All right, so The last example that I'll talk about is the scalar-scalar case, because scalars are nice. They don't have spin, so you can actually kind of uniquely fix everything for the scalar case. So if you just take the non-relativistic limit of the amplitude, what you end up finding is that you get a piece that scales like the Yukawa term, and then everything else is just going to be delta functions or even numbers of derivatives of these delta functions. So as promised earlier in the talk, I mentioned that I threw away the delta function terms for the pseudoscalar potential, and part of it is because I was going to talk about them here. But you can essentially show that you end up getting the same behavior, right? So you take this delta function term, you hit derivatives on this, and what you end up finding is that the number of derivatives that you're acting on this with will determine the power divergence of the R that you have. But it'll also determine the coefficient that you have out front. So in particular, if you don't have any derivatives, then the coefficient that you get is just delta of R to the L plus L prime with no coefficient out front. You plug in the zero states, nothing blows up. If you hit it with n equals 1, which gives you two derivatives acting on this, you end up finding that for the states that end up essentially being pathological are going to be L and L prime are both 0, or L and L prime 1 is 0 and 1's 1. And that's actually exactly what's going to be killed off by this coefficient term out front. And so you essentially end up finding that you basically get all of the terms that are there in this non-relativistic expansion end up working out exactly fine, and you get a well-defined answer. And a similar story can also be told for the scalar fermion case, where the unique low energy or the unique non-relativistic limit of the amplitude has a similar term where you are have a new function g of q multiplied by the operator q dot s, because that's basically, in the case of scalar fermion scattering, you only have one spin, so the only thing that you can dot it into is a q. So you get another term, and then you can essentially do a similar analysis, and you essentially end up finding that things that have replace basically all of the 2n's by 2n plus 1, and then the rest of the analysis sort of carries through. Okay, so just to kind of throw up some conclusions about kind of what we're doing on a large scale. So using the field theory, we came up with this framework which allows us to set the boundary conditions at some finite radius, and it allows you to kind of look at a larger scale, a variety of different potentials. And the upshot is that it allows us to reproduce known results for the Yukawa potential, which then allows us to also, say that, all right, this is probably not something that is completely wacky. So we can actually use this to analyze potentials where we no longer have this freedom. And so we do this for pseudoscalar potentials, and we find that you don't generate any Sommerfeld enhancement. So tree level scattering is actually a good approximation. More broadly speaking, one thing I didn't talk about was the axial vector potential, but you can do a similar analysis. And basically, for axial vectors, if you're working in kind of like the pure axial vector limit, where you've decoupled the scalar Higgs mode that comes along, in those theories, then you also don't generate any Sommerfeld enhancement. But the fact that you have a scalar Higgs mode means that there's regions of parameter space in that theory where you can basically make the scalar light, and then you can generate Sommerfeld enhancement from the scalar part of it. So there's some interplay there in that theory where you kind of have more particles flying around, more mediators, so you have a little bit more freedom, but kind of in the pure axial vector limit, there's arguments that can be made which essentially tell you that you're just not going to generate any Sommerfeld enhancement either. And then kind of abstracting away a little bit, it's kind of telling you that the quantum mechanical potentials that we're generating from field theory are very non-generic. So there's some operator structures that are kind of giving you these miraculous cancellations to kind of help come in, essentially save the day and give you non-singular behavior for these potentials. And so this naive classification that people have come up with, is not sufficient. You need to actually figure out a more precise, way of delineating what the boundary is between the potentials that are singular and not. And so some of my work has been, so far I've kind of thought about this on tree level, but in terms of like future directions, this is one of the future directions I'm thinking about, which is to, figure out exactly how to, how does this story generalize when we start including loops in the story? So if you have a loop refined potential, where does this interplay, kind of break down? How do we refine the criteria for determining what is singular or what's not, so on and so forth. And then on the more kind of phenomenological side of things, where we're interested in kind of how this goes, so far in this entire story that I talked about, I really only focused on the scattering case, right? And it's sort of a natural next step to consider, how does this behave when we start thinking about annihilation? And the only kind of like new features that come along for the ride are basically the fact that annihilation is an inherently short range process. So you expect there to be, some contribution of that annihilation part in the short distance boundary conditions. And it's also imaginary because it's going to be an absorptive piece. So there's sort of like the new features that kind of come along. And then, just kind of thinking again back towards the case of scattering, if you have cross sections that are large enough, then in a lot of these subhalos that we're looking at around the Milky Way, you may potentially trigger gravithermal collapse of these subhalos. And essentially what that amounts to is, you can change the density profiles based on kind of what you would naively expect. So an interesting question that we're kind of thinking about now is, does this leave astrophysical signatures that we can search for? And, if they are, can we use the current observations of subhalos that we have to place some interesting constraints on kind of the parameter space of some of these SIDM theories. So it's kind of currently where I'm at in the landscape of things that I'm thinking about. So, thank you.
Questions? For the last thing you said, like you're looking for signatures of, basically density spikes.
Yeah.
The center of small halos, like the model dependence here would come in because like you get this at different like mass scale, like subhalo mass scales.
Yeah.
Is that it depends? So when you're tracing back to like your model building, that's how you.
Right. Yeah. So depending on kind of the subhalo masses you're looking at, you're effectively probing this gravithermal collapse occurring at different mass scales. And so the idea would essentially be that the way these models kind of feed into it is a timescale for this gravithermal collapse to occur. So if the cross sections are very high, then you would expect the timescales to be shorter. And so then the idea is that for objects that are really, really tiny, the cross sections should be Sommerfeld enhanced to be relatively high if we're talking about the Yukawa case. So we would expect the gravithermal collapse to have occurred earlier in the evolution history, whereas if we're looking at really massive objects, then on average, you're expecting their virial velocity to be high, so the cross sections are low, and therefore they may not have undergone gravithermal collapse. So basically, the way of tracing it back would be essentially to use those constraints to kind of to put constraints using that. Not yet. Not yet. Yeah, I mean, but like part of the, I'd be interested if someone can find it, because then that tells me like, okay, the criteria that I have is too simplistic and I need to refine it. But so far in terms of the analyses that I've done, I haven't found anything that's caused it to break down.
Some cases of non-central here, just good examples of one of them.
Yeah. What do you mean specifically by non-central? Because technically the pseudoscalar potential is non-central, right?
Yeah. So that's one particular example.
Yeah. Yeah. So I mean, like in terms of cases that I've tested, some of the scalar fermion examples will be non-central because there's a Q dot S that's kind of breaking that rotational invariance. Anything that has one of the interaction vertices being a pseudoscalar type interaction. So you could consider kind of like the cross cases where you have different particle species. So what you're considering is a scalar vertex on one side and the pseudoscalar vertex on the other side. And you can look at that, and that would also break the rotational invariance and give you a non-central potential, and those ones are still fine. So they still give you something that's not pathological.
So what is boundary that you match things? Do you assume that it's low enough R that your Born approximation is good, but then high enough energy that you're like, things are being modified enough. Like what exactly are the boundary conditions that you impose?
Yeah, so the boundary conditions that you need for solving the Schrodinger equation are basically the value of the wave function and its derivative. So what I'm using is so what I'm essentially saying is that in this annoyingly enough, the red region, which is supposed to be the UV. I don't know why Ask Me made that choice, but we did. So in that red region, we're basically saying that there is no significant Sommerfeld enhancement. And so essentially taking a tree level answer is sufficient in that region. And we're using that to then determine how the wave function is being altered via this K matrix.
Okay.
And so then once you have that, you can then basically say, all right, I know what the wave function and its derivative are at R equals A, and then I can just solve the Schrodinger equation outwards from R equals A to infinity.
Okay, but how much do you assume about the region of the deep UV region?
There is flexibility in there. So that was one of the, like numerically, that was one of the things we checked where we basically allowed R equals A to vary. So 1 over m chi to vary between like 0.1 to 10 over m chi. And you end up finding that the results are fairly robust as long as as long as you're not getting to the stage where you're getting to 1 over m phi, which is the mediator mass. So as long as you're not kind of getting to that regime and you're allowing those things to be parametrically separated, it's fairly agnostic to exactly where you're setting the boundary conditions. The answers that you get at infinity for the S matrix, or I mean, the cross section that you're getting at infinity is fairly agnostic to exactly where you're doing the matching.
But can you tell things about the DPV from your IR constraints? Like,
so I mean, in terms of like, if we were to map it out over different velocities, you would then be able to tell what works, and then you could then back that out into like a particular set of model parameters, if that's what you're asking. So in terms of that, like you can take IR data, which is what you're seeing from the scattering limits of from galaxies and dwarfs and stuff today, which is deep in the IR, and then you can use that to kind of back out what the UV model looks like.
thanks.
Other questions? No, this